So 10.1, hopefully you've already watched the lecture video, so I'm going to work through some examples from homework. So let's begin by taking a look at this one. It asks us for the domain of f of x equals the square root of x. So when we're looking for the domain, remember we're looking for what x values can we plug in and get an answer. So if we were to make a table, if we plug in 0, we can take the square root of 0. The square root is asking us what number times itself makes 0. So 0 times 0 makes 0. If we put a 1 in, 1 times 1 is itself, so the square root of 1 is 1. If we put in a 4, 2 times 2 makes 4, so the square root of 4 is 2. What number times itself makes 4? Or also, what number to the second power makes 4? That's why it's called a square root. What number, when we square it, makes 4? Now, numbers like 3 don't have square roots that are integers, but we can still take the square root of 3. It just comes out to be a decimal. If we put that in our calculator, the square root of 3 gives us a decimal that goes on forever and ever, and it doesn't get into a pattern. So the square root of 3 is about 1.73. Now, that is referred to as an irrational number because we can't represent that as a fraction of one integer over another one. But all of these numbers have square roots because when we take a number times itself, it gives us what's under the radical. But if we look at a number, for example, let's do -4, because we know what the square root of +4 is. But if we put a -4 underneath the radical, is there a number when we square it, or in other words, when we multiply it by itself makes -4? Well, if x is a positive number, when we do a positive times a positive, that makes a positive, so that's not going to work. If x is a negative number, a negative times a negative is positive, so that's not going to work either. So negative numbers don't have a square root, at least not a real number square root. So when we take the square root, we can only do numbers that are bigger than 0 or 0. So x is either bigger than 0 or it's equal to 0. As an interval, the domain starts at 0 and goes to positive infinity. We include 0 because it is okay to take the square root of 0, and we go to positive infinity. So that's our domain. So over here, we'll just select the option that says 0 to infinity. And that's going to be true of any root that's an even root, whether it's a square root, a fourth root, a sixth root, or whatever. Now the next question asks us for the domain of the cube root of x. And since a cube root means what number times itself makes whatever is underneath. Well, when we cube numbers, if x is negative, we can cube a negative, and a negative times a negative times a negative is negative. And if we cube a positive, 3 positives make a positive. Or if we do 0 cubed, we get 0. So in other words, when we cube numbers, we can get negatives, positives, and 0. So what kind of numbers can we take the cube root of? Well, we can take the cube root of anything. If it's a negative number, we can get a negative number by multiplying a negative number to the third power. If it's positive, we can get a positive by taking a positive number to the third power. Or if it's 0, we can do 0 to the third power. And that's going to be true anytime our index is odd. So if our index is odd, our domain is all real numbers or negative infinity to positive infinity. All real numbers. So that's our domain. So now let's work through some problems. So let's do this one. The square root of 100x to the 6th. So, quick reminder, remember when we are multiplying and our bases are the same, we add the exponents. Okay? So, when we take the square root of this, what number times itself makes 100? Well, 10 times 10 makes 100, so the square root of the number part is 10. For the letter part, when we do the square root of x to the 6th, x to what power times itself makes x to the 6th. So these have to be the same because we're taking a square root and we're looking for something times itself. When we add these exponents together, they need to add to make 6. So if what number plus itself makes 6? Well, that would be 3. So underneath that radical, we could call x to the 6th x cubed squared. Remember, when we have an exponent to a power, we multiply those. And from the video, one thing that we were told is if we're taking the square root of something squared, those undo each other. So we're left with 10x cubed. Let's do another one. Let's do this one. For a cube root, it's going to start out by asking us to take the cube root of a number that's a perfect cube, and then we'll get into some that are not perfect cubes. And if it's not a perfect cube root or a perfect square root, we would just have to use our calculator. So let's start out. If we do 3 to the 3rd power, 3 times 3 is 9. 9 times 3 is 27. Well, that's not nearly as big as that. So let's make it a little bigger. Let's try 5 to the 3rd power. 5 times 5 is 25. If you take out your calculator and do 25 times 5, that's 125. So that's getting closer, but that's still not as big as this. So let's try 6. 6 times 6 is 36. And if we do that times another 6, we get 216. So the cube root of 216 is 6. So it's good to carry around numbers that are perfect cubes. And we talked about that when we were factoring difference and sums of cubes. We probably didn't quite make it up to 216, but 216 is a perfect cube. It is 6 to the 3rd power. So let's do another square root. Let's just do a single variable factor. So remember, if we have something squared under the square root, those undo each other. So we want to write this as something squared that makes x to the 8th. So remember, if we have a power here and a power here, they multiply together and they need to multiply to make 8. So what number times itself makes 8? Or I'm sorry, what number times 2 makes 8? 4. 4 times 2 is 8. So when we take the square root of that, the square root and the square cancel. So we get x to the 4th. if we have multiple variable parts, then we just do the same thing for both of them. We rewrite x as something squared. We write y12 as something squared. So for the first one, our exponents need to multiply to make 4. So what times 2 makes 4? 2. For the next one, and that's supposed to be a 12 or a 2. What times 2 makes 12? 6. So we've expressed each of these as something to the second power. This squared and this squared. So when we take the square root of the first one, the square root and the square cancels, giving us x squared. When we take the square root of the next one, the square root and the square cancel, leaving us y to the 6th. And if you want to check, how would you check to see if that's right? Well, when we multiply this times itself, it should give us what we started with. So if we do that times itself, that means we're raising it to the second power. If you'd rather write it that way, you can. You can write it as x squared y to the 6th to the second power. That would actually be shorter. If we do it the first way, we're multiplying and these bases are the same, so we add those exponents. 2 plus 2 is 4. We're multiplying and these bases are the same, so we add those exponents. 6 plus 6 is 12. That's what we started with. If we check it this way, remember when we have a product, each one gets the exponent. So we have y, or x squared to the second power, and y to the 6th to the second power. If we have two exponents like this, we multiply those, so 2 times 2, and 6 times 2. So yes, either way we do it, it checks out. So that is the square root of x to the 4th y to the 12th. Now let's do a cube root. So we're going to use the same principle. So we're going to rewrite each piece underneath the radical as something cubed. Because if we have something cubed under a cube root, the cube root and the cube cancel. So we want x to what power when we cube it makes 9. Remember, these have to multiply together to make that. So 9 is 3 times 3. These have to multiply to make 15, so 3 times what makes 15? Well, 3 times 5. So when we take the cube root of this, that 3 and that 3 cancel, leaving us x cubed. We take the cube root of this one, that 3 and that 3 cancel, leaving us y to the 5th. Very good.